Pavlos starts off. Pavlos is one of the reasons why we are here today. So thank you, Pavlos. Pavlos is Pavlos corrected me yesterday, the scientific director for the Institute for Applied IISC, Computation Sciences, right? Perfect. So which, to me, it means that everything applied, which primarily means these days machine learning and AI, Pavlos runs the department by that name at Harvard. Pavlos and Rahul are colleagues, and long ago and far away, when I started looking for people who would collaborate together to do this, I found Rahul through a mutual friend of mine from undergrad, and through Rahul we found Pavlos. So we've enjoyed a lot of support from both Rahul and Pavlos in sort of creating and taking this venture from where it was a year and a half ago to today. So thanks very much, and over to Pavlos.
Okay, thank you very much. Thank you for inviting me. I'm excited to be here. So I just noticed that I'm the only non-Indian speaker. So no, I was the first one here. I said, not giving a talk. So I was right. My guess is that they look at me and said, "Brown enough. Invite him." So that's why I'm here. Okay. So I'm talking about, actually I'm very excited to be again. This is my second time in India the last 6 months. It takes a little bit of used to at the beginning, but it's a lot of fun. And I like the people here, and the food, and other things. All right, so my title of the talk is just to intimidate everybody. That's the main goal. I put every keyword I could imagine that it sounds funny, generated, adversarial, augmentation, and eventually I throw Wasserstein too. So the goal of the talk is to demystify this. We'll talk, as the other speakers, kind of more building it up. And a lot of you will be here for the next 2 weeks, so if you don't like me, this is the time to run away, because I'll be your main lecturer for the next 10 days. So this is a test. All right, so I'm Pavlos Protopapas. Met Sid and Rahul. Actually, I know your friend. That's true. So we have two connections, two graphical models. You can model that, right? So I know how to do that. All right. So let's start with an outline. So I will try to motivate why I'm doing this. Basically, let's go back to my title. The main thing is that we do data augmentation. So Sid introduced me as an astronomer. I have multiple hats. At the same time, being the scientific director at the Institute of Applied Computational Science. We're a data science shop, basically. But mainly my research is at the cusp between astronomy and machine learning. So I apply, or statistical learning, whatever you want to call it, I apply these techniques to astronomical problems. So I want to do data augmentation in astronomy, so you may wonder why. So I'm going to try to at least motivate it. By the way, these lights are not friendly for people, they're bold. You just emphasize my boldness. All right, then I'm going to try to explain deep generative models. I'm going to try to go actually down to the basics. And my goal is that at the end of the talk, at least you know, besides being super hungry and hate him, not me, understanding what is GANs and what is this generative models all about. And once I get there, I'll explain our model and show you some of the results. But my main goal is to motivate and explain the methods, okay? All right, so let's look at the motivation. So there was a discussion earlier about how these deep neural networks on machine learning become very successful recently. And we're talking about, I think Rahul mentioned about the computational power that is available. Some of the algorithms, as we all know, they've been there for a while. So let's start from the beginning and build it up. So there's two types of machine learning, the supervised and unsupervised. Mainly I'm talking about supervised here, which seems that it's the majority of machine learning exercises we do. And to do supervised learning, okay, this is simple. I'm using what is called RAM-up. I'm going to start easy, and at the end of the talk, it's going to get a little bit more tricky, okay? So supervised learning, you need a training set. And we know very well that the bigger your training set, the better your model it is, right? So supervised learning is that you show the machine some examples, and the machine learns from those examples, and then it becomes the model that you're going to use. So it makes sense. I mean, it's intuitively, more examples we give, better it's going to learn, right? So you see in this graph here that as the training examples, the training set becomes bigger, your performance, which is the cross-validation performance, which is the green one, goes up. Now the red goes down. Can someone tell me why? It should be obvious, but let's make it a little more interactive. Even though I cannot see you, I see a white blob in my face, but I can imagine. Yes, over there.
Basically, you want to reduce the bias in the training so that it will not just fit for the training, but other kinds of data.
Yeah, so reducing the bias, he says, he's trying to use fancy words like me. Basically, if I have one example, I'm going to learn it very well, right? I have two examples. As the number of examples increase, the model becomes more complicated to learn, right? So that's why we see going down, right? Is reducing the bias, exactly what you said, right? So let's move on. So one thing I want, so bigger the data set we have, better it is, right? Bigger the training set we have, better the model will be. We've been hearing a lot about having huge data sets. But the problem is that these data sets come with no labels, right? So I take a bunch of pictures on my cell phone. It doesn't always have a label. I don't go and say, okay, it was a cow, this was a cat, right? We don't put labels. So overall, we have a lot of data with no labels, right? So in order to train these amazing models, we need actually training sets. And training sets means we have labels. So I give you another example to motivate that, is the following, that if you look at the statistical machine translation algorithms, were introduced late 80s. The big success of the machine translation is only happened the last 10 years, right? I would say the last 5 years they become reliable enough that if someone writes to me in Spanish, I can use Google Translate to understand what the content is all about, right? And this happened somewhere, actually the big revolution happened around 2006, 2007. So why is that? The algorithm was there. You may say it's the computational power, but it's not only the computational power. What is also the case is that we have a lot of training data now. And what happened here is that Google has realized that there's a lot of websites that they translated from one language to another, right? So that means I have one language with one label and I have another language with another label. Now I have a training set, so I can train all these amazing algorithms that will be sitting there for so many years. It's actually funny enough that for a while the performance of the machine translation was going up and then it went straight down. Can someone tell me why? Have a guess. Yes, back there.
Grammars.
What's that?
The grammar was different for both languages.
The bandwidth, you said?
The grammar was different for both languages.
The grammar was
The grammar. No, it wasn't that. It wasn't the grammar. Diversity of data. No, it's not even that. It's even simpler. Google was using the machine to translate, finding these translated websites, using them as a training set to learn the algorithms. So they're translating with their own translation, and then they were thinking, "Ooh, I have this website which is in both language. Let's use that to learn." But it was spiraling down.
Overfitting.
Yeah, well, it's overfitting. I call it spiraling down. It's like this thing is happening now. This talk. Okay, so the same happened with the convolutional neural network algorithms. I think in the previous talk you referred to the actual paper. This happened in the 80s, right? Nothing happened for 25 years until ImageNet became available. which is basically about 1 million images. People manually label them. Once that data set became available, boom, we have this amazing image recognition algorithms. Convolutions, they were there, they were sitting for us. It's the training set that actually make the difference. Plus the computational power, plus the algorithms became fun. I'm not saying is the only one, but it was a big factor. Having the training data enable all these big things we see now. Okay, so I hope I convinced you that we need training sets, right? Yeah, well, everybody's convinced. All right, so now the next question is, all right, so we're convinced we need data set, training, we need labels. How do we actually label data? Okay. So I'm going to just describe the 4 methods I think are there to train data. So the first one is manually or visual inspection. So I have images of dogs, like here. See that, right? And I sit down and I say it's a dog, and manually visual inspection, right? I'll tell you a funny story too. So when I started this business, machine learning, I was long time ago. Some of you are not even born. So I had a data set from astronomical images, and I was supposed to label them. There was a lot of them, and it was boring. So I was home, and my mom, who is a teacher, ex-teacher, I mean, she retired, she had nothing else to do, so she started manually label things. I told her where to look for it. So my mom was labeled things. So I have the first training set ever been done in astronomy by my mom. In the meantime, she was doing lunch for me and dinner because it's a good Greek mom. All right. So in the absence of good Greek mothers, we have to find something else, right? So manual visual inspection is good, but it's expensive. So sometimes we use crowdsourcing. Okay. And did I hear a phone? I think I heard a phone. Another way of doing that is a little bit more intelligent than having the Greek mothers, which is basically you ask the model, where are you confused? I'll give you more labels, right? So if let's say I classify cats and dogs, and you have an English Shepherd there who is a dog, and you have that little dog that looks like a cat, the model gets confused there, and is asking you, tell me if it's a dog or a cat, so I can learn, right? So that's called active learning. Okay? So that's another way of doing it. So you get the human to label, then the model tells where he has problems, you bring the human back in to label, and you keep going. Okay? Yet, these 2 methods involve humans, and it's been my experience with humans are very complicated beings, machines, right? So they don't behave as you expect, so we want to do something different than that. So the other one is to synthesize. So if I synthesize the object, so if I play God here and I synthesize objects, I know what they are, so I have the labels for free, right? So let's say cats and dogs, to that example. If I'm making cats and dogs, I generate them, I know I make a cat, so it has a label. I make a dog, it has a label, so that's good, right? Okay, the problem is being God and synthesizing things, and that's what we're going to be talking soon. And finally, it's called transfer learning. That's trying to learn from one domain to the other. So if I learn the language in German, maybe not German, in Spanish, the knowledge I'm learning about Spanish can be used to learn Italian. Okay? So that's called transfer learning. Well, today we're talking about that. So what we're going to be doing, we're going to synthesize data, we're going to generate data, right? Okay, it goes back to the previous talk about generative models. So we're going to be talking about the same ideas now, how we generate data. Okay? Any questions so far? We're good. All right, so far we explained the motivations. Now let's talk about generative models. We call them deep generative models, but let's start by explaining what a generative model is all about. So before that, let's just make it a little fun. Why do we care about generative? You hear about generative models. Rahul even said, we're going to have the advanced things in October with cool things such as generative models. What on earth are these generative models and why they're cool, right? Okay, so generating data could be exciting. So I can make fancy anim. Ooh, so if you're into these kind of things, what better than making fake ones? I don't see the point, but that's okay. Well, you can also make faces of celebrities. Thank you very much. I'm a celebrity in some circle between my daughter and my son. Maybe. All right. So this is from NVIDIA. So these are not real people. Eh? These are fake. I mean, except me. The rest are fake people. Okay. So it's amazing. You can make these kind of things, or for some of us, not all of us, you can start by creating even generative fashion. Useful. I said for some of us. I don't want to put on anybody there, but sometimes someone helping you how to get dressed could be helpful for some of us. All right. So this is an application I found. You get the model. You get some points here. This is the ground truth, and then it generates some kind of putting the jacket on and what kind to wear, right? Or you can make music. I'm sure you've seen some of these examples. So this is a problem. I'm working with a student at Harvard. He's from the design school. So sometimes, why do you want to generate one? And I think that goes from the design of clothes I was saying before, is that let's say you want to build a house and you don't know how to design it. So what you do, you give the footprint or you give the area that you're gonna do, and this thing just generates a bunch of plans and designs. Actually, it does rendering, it puts furniture, the whole thing. And it's not that you use that in order to build a house, though I've seen some houses that this will have done better. But a designer can just now see a number of them and then takes one he likes and continues from there. So it's like an intermediate suggestion. That's how we're using it for this one. Okay. So another thing that is pretty good, generative models can be used, is something called transfer learning, style transfer, I mean. And I'm just going to give you some examples. I think we already have seen one in the first talk. So you take an input, which is a painting, and then the style transfer makes it into a realistic photo. Another example is, I really like this zebra and horse. It's a donkey, no, a horse. So you get an input, you get a horse, and you make it into a zebra. And then you have two horses, and you make them two zebras. A horsey upside down, a zebra upside down, great. And you can do the opposite. You start with a zebra and you make it into a horse, and they can play. But the most amazing, this for me, is the apples and oranges. You know the expressions, don't compare apples and oranges. You get this, you can compare them because you can switch from one to the other. The word is getting confusing. I don't know where things are going with this. But this is called style transfer. It's pretty amazing. And this is a cool one. They make actually a video out of this. Another style transfer is you go from winter to summer. Okay. This is another super cool application for generative models. Is pick to pick, so you get an outline of a shoe and it makes to a shoe, or the cat, etc. Okay. This is, again, you get the segmentation, you get the segments, you just kind of draw that, and then it renders it into a realistic image, right? So there's many cool applications on that, but I want to move on. I think we're all getting hungry, and I want to spend time on it. The other one you can use generative models is for signal super resolution. This is an example. You start with an image. Some of your cell phones are using that. So you take an image, even if you shake a little bit, they use these generative models in order to get into higher resolution. All right. So finally is the data augmentation. I'm going around and around. Why do I care about GANs? And I told you at the beginning that I want to have bigger training sets. And I told you at the beginning, in order to have bigger training sets, one of the methods besides the manual inspection and labeling, one of the methods that I was going to focus is the data augmentation, right? So this is what we do here. It's the most boring of all, I'm sorry. It's just a time series. So these are time series from stars. And what we have, and this is the problem statement, is that we're trying to do either classification or characterization / regression of objects in the sky automatically. Okay, that's the problem. That's a task. The problem we have is that we don't have training sets for many of the objects. So we may have, for some rare objects in the sky, which are the most interesting, very few examples. So what we want to do nowadays is that we have all these new telescopes being built. The next few years we have even more. What we want to do is that to automatically characterize and categorize and do all these things of the stars and the objects in the sky. And the problem is that for some of them we don't have a training set. So the whole point now is to automatically generate and augment our training sets with these methods. Okay? That's the thing. So that's why we care about data augmentation. Now, so let's recap. We want to have training sets. I think I explained. How do we do it? I said 4 methods. The one that we want to use is with data augmentation. I cannot motivate generative models in the coolness factor. I think I showed you enough cool things. But let's now go and understand what we mean by generative model, right? Some of you know very well. Some of them, you heard already the word generative models. I'm just going to break it down for you, right? Okay. So generative model for me has the following meaning. Let's say we want to generate data from a distribution. There was a talk that actually touched it very well. So you get this thing, and I'm generating data, and then I have the observed data, and somehow magically I'm going to make them match by changing my generating model to match the other one through a likelihood or something. Okay, so let's get the simple idea here. So what we have, I want to generate data from some distribution P of x. So here is my statement. And for example, let's say I want to generate data from a distribution that looks like a bell shape, the normal distribution. Okay? And the question is, how do I generate data coming from that distribution? Anyone? So if I ask you, okay, get your laptop now and generate data from a distribution that is normal distribution. How many of you know what to do? So how do you generate? How do you apply the normal distribution? Yeah, you know the answer. If you know the answer, don't tell it. Trying to guess, that's the game we play. Try to guess. Most of you think, numpy.random.norm, right? Give me the data. Right. But the actual thing, you generate data that those data follow a distribution is not the PDF that I'm looking for. It's just get a bunch of samples that if I get the histogram will look like a normal, right? Okay. So one example is that, or let's say I want to do the exponential, and the answer is coming. Thank you. So how do we do that? So I know how to generate data from a uniform. That's easy. For example, ask the computer to give you the time at microsecond or millisecond. Microsecond is better, nanosecond. Every time I ask that, it's most likely a random number that comes from uniform. Okay, we know how to do that. Now from there, moving to the next stage, which is getting to be a distribution I want. So I do the uniform. Thank you very much. So the next thing is that I'm going to take this data, and I'm going to do something to that data, such as to give me the distribution I want. Here I have the data to be drawn from the exponential, minus exponential, right? So I'm taking the z, and I'm going to step on them, I'm going to punch them, I'm going to spit on them, such as whatever I get out follows this distribution. Okay? So I have some function, which I call f, which I'm going to apply on the z, such as when I do that, it gives me that. All right, so what is that function? Any guess? Except you. The what? CDF of that. So you integrate that, you do that, you invert it, and bam, you get the logarithmic, okay? All right, so that, for this one, it works. You can do the math very nicely, right? And you end up with the log. But if this distribution here was something complicated, you can't do the CDF, you can't integrate the thing, you won't be able to do that. However, the home statement is here, that there is a function that is going to map my uniform data to whatever I want. Okay? And how do we find that function? Sorry? what is the machine learning exercise that we know that is really good at approximating nonlinear functions? Sorry? A neural network, thank you very much. Yes, exactly. So we're going to approximate that mapping with the neural networks, right? And, So, it's exactly what we say here. So let's look at it. Right? So I start with some uniform number. Okay? I pass it through some neural network, which I call generative model. And it has some weights, and it generates some distribution. Okay, so I start with any. Now this function here, this mapping here, it just starts with some uniform and gives me some junk, right? But I want it to look like this. So now I'm going to compare this to this and say, you're doing well or you're doing badly, right? Okay, so I'm going to now be adjusting the neural network, the weights, the function, in order for the pink one to look like the blue one. Right? So that's the end of the game. That's all. So I adjust my network in order to give me the distribution. And well, neural networks are pretty good at finding this mapping, and that's a generative model. Okay? So I demystify one of them, right? So what we call, when we compare the distributions here, how do we compare two distributions? You can use any kind. You can use cross entropy, or you can use scale divergence. The common one is to use scale divergence. So any metric that measures the difference between two distributions will work. Okay. So I think we understand now. Let's talk about GANs, generated adversarial neural networks. So I think we understand what the generative model is. Now let's just make it adversarial, right? So we are here just a minute ago before I step to the outline. So I said, okay, I'm going to take some uniform numbers, I pass it through some function, which is my neural network, it gives me something else, I compare to here, and then compare these two, I decide if it's doing well or not, and then I inform the network to adjust in order the pink to be as close to the blue one, right? Are we with me? Yes. Okay. You know what is my favorite emoji? There is one that is like that. I never understood what it means, but when you feel happy with me, can you do this? So I know you're following me, right? Okay. Okay. So I'm going to do something now into the generative model. So I'm going to put it up there, and what I did, instead of comparing the two distributions here, I'm going to take that loss function, which I use scale divergence or cross entropy, I'm going to change it now to something else. I'm going to put another network which goal is to learn how to compare two distributions. And this network is a discriminator. So the job of this is to say if it's blue or pink, if it's real or fake. Okay? So that's all it does. So this guy starts with a random number, generates something, it's either real or, it's the fake one, and this one here will say it's a real or fake. That means that if this network here does an amazing job on generating something like that, this network will be having very hard time to distinguish between the two of them. So that means the generator does very well, right? If it does poorly, then this one would know. Right. Now remember, I'm going to be learning this too, because this may not be a good one. You may present, let's say the blue are dogs and the pinks are cats. I may present a cat to this one and said, yes, it's a dog. Right? So I need to learn this and this at the same time. Let's look at an example and you'll understand. Right? So let's say my goal is to generate a time series that looks like that. Think about this like you're a dog or a cat, right? So my goal is to create a generator who is going to generate a time series that looks like this, right? So I start, and remember this one is not trained. It doesn't know what to do. It generates a bunch of noise here. The discriminator looks at this and it says fake, right? So it says, it decides it's from the generator. And now I have to inform this network here that something is not right. So I do my derivatives, and I tell this generator, we'll learn all these things in the next 2 weeks. We let the generator, hey, you're doing something wrong. This is the direction I want you to change. So the next time around, it does better. Here, the discriminator, which is like a parent, he says, you're doing badly, but I want you to do it this way, still informs the generator, you're not doing a good job. Please change your weights in this direction to do better. And now at one point, this is getting full, right? Now I have to inform this guy, hey, this was a fake one, get better. And now you get that better, and the story continues, right? So we have two things competing. The generator is trying to fool the discriminator, and the discriminator is trying to find out if it's fake or real. It's an amazing little game, okay? So it keeps going until they both get better. And then that's where... So this is another drawing to see. So I start with some random numbers. The generator generates... Here I'm playing with the digits instead of time series. The generator generates some pictures that they look like digits. And the job of the discriminator is to discriminate between the fake and the real one. Okay? Is everybody with me so far? Are you getting hungry, right? Yeah, I'll try to go live.
What was the arrow on the right?
This one?
No, the one before that. Yeah. When the true distribution tells above.
Sorry, can you repeat the question?
When the true distribution points to the arrow above and tells it to correct. You go a slide.
Here? Yeah. So what I did, I gave a fake one. The discriminator got full. So now he has to improve itself. So it's going to get better at distinguish between fake and real one, right? So that's why I'm saying there's a two-man's game here, two people's game. So at one point, this has to get better at discriminating between this and this. Because as you see this one, it looks like this, but it's quite obvious it's a fake one, right? So now it's getting more interesting, right? Okay. All right, so there is a loss function that it has two parts. The first one, this is the outcome from the discriminator. So this is like the cross entropy of the discriminator. I'm summing over all the real ones that I'm going to present to the network. So if this is not correct, this should always give you 1, because what I call real 1 is the real ones. And these are the fake ones. I'm going to sum over the generator, the fake ones, right? So the discriminator seeks to predict 1 on the training samples. So it's trying to maximize this, right? Because if I give, for each real one, I give 1, that means good. So I'm trying to maximize this. And at the same time, the discriminator wants this to be 0 because they are the fake, right? But the generator wants this to be predicted as 1s. So I minimize the loss function here with respect to the generator, but I maximize this with respect to the discriminator. So these are the weights of the network for the generator, and this is the weights for the discriminator. Okay? So what do we have? We have a min-max game. So one is trying to minimize, the generator is trying to minimize this loss function, where the discriminator is trying to maximize the same loss function. Okay? So training GANs, though, it looks very nice. I mean, it's a simple idea, right? So we have two things trying to compete with each other, and we know competition brings the best out of all of us, maybe. But there is a couple of problems here. So the first problem is very, very hard to train these things. So I'll explain as we go along. So this is just quickly, we did this example with trying to generate Gaussian distribution. My generator is just 2 layers of fully connected network. The discriminator is again 2 layer plus the output layer of fully connected layer. Normal neural networks, and what you get at the beginning, here is what the generator generates, and as the progress goes, he goes towards this one. Okay? So you can see the game how it's played, right? You can also do it with convolutional neural networks instead of fully connected. This is the architecture. Now, just want you to pay attention in one little thing here, because I can say, oh yes, you can do convolution neural networks, but notice that convolution neural network, you start with a big image, and as you convolve slowly, you get smaller and smaller and smaller. Here is the opposite. Okay, it's kind of deconvolution or transpose convolution, actually, better term. So you start with some random numbers, and then you generate an image. Okay. So I have been reading that studies show that if you have some pleasant thing between, it makes you feel better and you learn better. So this is a commercial pleasant break. So you can say, ooh, come on, it's a cute dog cat. Yes, all right. Now you're ready for my next part. Okay, so there are challenges. The biggest challenge is practice is their sensitivity to all these parameters we're going to be using. How many layers, what is the activation function, all the things that the hyperparameters are very sensitive. Also, there is another big challenge here is that there is no proof that they will converge. It's just hope for the best, right? And there is not, as far as I know, until a few weeks ago I was reading the literature, there's no proof. The only thing is that if they perform very well, so you use them at your own risk. Okay? And the best way to train a GAN, Generative Adversarial Neural Network, is to use a graduate student. Never do it yourself. That's what I learned. Okay? So there's more real challenges. One is called model collapse. So for example, if we want to generate images for faces, if the generator somehow finds one image or a family of images that will be fooling the discriminator, then the generator stops learning and you just keep presenting the same thing. So in this example, what they're trying to do is generate realistic faces, but this particular face always fools the discriminator. So the generator says, hey, I'm done. You're never going to get me, right? So it stops learning and it keeps generating the same image. But we don't want that. We want the generator to generate diverse faces, right? So what you do basically, when you get into troubles like that, what do you do?
Add some noise or randomness?
You add some noise, okay? So where I'm from, when I get into troubles, I ignore them. I don't know how is the ethics, the work ethics here. We ignore them until later. Okay? So that's what you do. No. So what you do, you just add some noise, or what you do, you put a penalty function. So you look at the diversity of the images that your generator makes, and if it's not very diverse, you penalize. Okay? All right. So there is a lot of what do they call GAN hacks? There's a lot of hacks that are out there to help you train the things, right? I'm telling you, it's kind of hard to train, but there are hacks there and people that be using it, and the successes, when you get it to work, is amazing, okay? So let's say the evolution of GANs, 2014, this was the kind of generating images they could do. By 2015, a little bit more realistic, but a little bit freaky. 2016, it's getting better. 2017, and then 2019. Sid is telling you he came to Harvard and got me. No, I'm fake. He generated me. I'm not a real person. Okay. And so this is the number of papers. You can see the archive that was happening since 2017. And one of the inventors of GANs, Ian Coldfellow, he noticed something that when you trained your GAN, if there are memes into the thing, the generator thinks that the meme is part of it, so it starts generating fake cats, but with the memes fake. I don't know. It's fake. It's not a language, that thing. It's not some strange language. Just gibberish, right? It's generated, right? When I showed it in class last time, students thought it was some strange language, but it's not. It just generate images that they look like letters, okay? So I also have what I consider kind of influential GAN papers. Start with the DC GAN. This is the Wasserstein GAN, which I'm going to explain a bit. Conditional, which I'm going to explain, etc., etc., etc. Okay. Now, GANs in astronomy, there's only 6 papers, so it's open field for me, baby. It's going to get accepted, whatever I submit. There's 2 ways to be smart. One, to be really smart, and there's 3 ways. The other is to be the first one somewhere. And the third one, which seems sometimes works for me, especially for exercise, is you outrun everybody. So, you know, if I continue running, by the time I'm 70, I'm going to be one of the best. Everybody else is going to be dying on my competition. All right. So we talk about everything. I think I gave you a good explanation, hopefully, what the GAN is. It's the 2 things, 2 people game. So I need to explain Wasserstein GANs 2, which I have a typo here, should be an E. And then our model and the results, right? So let me go very quickly explaining what these Wasserstein GANs are. So it's all about distance. When we measure the distance between 2 distributions, the way that the discriminator I described before measure, it just say yes or a no. So if you have a bimodal distribution and you start moving it, if it's far, for the discriminator is far. If it's very far, it's still the same. Let me explain this in a different way. So if I show you a picture of a cat, and it's obviously a cat, you say it's fake, right? But show you a horrible looking, I mean a really clear, like my cute cat I showed you before, is still a cat, right? There's no measure how far away I am from being real, right? So that means in the world of derivatives, there's no derivative to push back the generator or back to the right direction, right? So if you're far, right? So we're trying to eliminate that problem. So one way of doing that is to think about, you have, let's say you have one hill and another hill, and you want to see how far they are from each other. So you get a shovel, and you have to get all the dirt from one hill to the other hill, right? So if it's very far away, you feel it a lot. If it's not so far, you feel it less, right? So Earth moving distance, which is equivalent to Wasserstein distance, is the effort you have to do to move one hill to the other hill, right? So you can see that if they're very far away, you have to put much more effort to put it closer than if they're close. Where the discriminator I described before, it doesn't matter if it's far or very far or extremely far, right? So that gives you some kind of derivative. How far are you in order to correct it and make better networks, right? Okay, so that's the basic idea. And now instead of having a discriminator, they call it critic, because it's not yes or a no, it's, you know, it gives you a criticism, right? So it is very simple. It boils down to this following diagram. So let's say you have the fake and the real ones. The critic, what it's trying to do is separate the 2 distributions as far as possible, right? Basically, every image I get, so let me show you, actually, I'll explain this. Every image I'm going to get, or every input I'm going to get, I am going to map it to a number. Think about that. So what the discriminator used to do, it will say yes or a no. Think about the critic, that anything you give me, I'm going to map it into one number, okay, or 2 numbers. Let's say 1 number. Actually, let's say 2 numbers so I can make my diagram work. So anything you give me, I'll give you 2 numbers, and I plot it, right? So all the real ones will be blue, and all the fake ones will be red, right? So for each input I get, or each image, I'm going to map it to the 2 numbers. So the goal of the critic is to make the 2 separate as far as possible, right? Because if they're different, they're different. I can recognize the fake from the real. And the goal of the generator is to make them as close as possible. Now, because the generator has no control over the real one, it can only move the red ones, the fake ones, right? So what it turns out is that, if you look at the details, is that what the generator is trying to do is move everything to the right, and the other one moves everything to the left and right. Okay? So that's the basic idea, right? Does that make sense? And the loss function is very straightforward. So the critic is trying to make this as far as big as possible, these differences as far as far away as possible, where the generator is trying to push this guy on top of the other. Simple, right? So that's what Wasserstein distance is. There are complications, the mathematical complications, because you need that to be a function for things to work, in a particular kind of function, Lipschitz K function, and to do that you have to clip things, details, okay? Which we can talk later, but the point idea is that it's just trying to push it and the other tries to put them close. Okay, so I think we covered everything, and I stick one extra thing which I call conditional GAN. We haven't talked, and it wasn't there in the original outline, but I'm sticking it now because we have to talk about that. So one thing that we need to have is that sometimes we want to learn how to generate things, but we want to learn from many, many different representations. So let's say I want to generate animals. I can get a bunch of images of cats, and I can generate fake cats, right? Or I can give a bunch of dogs, and I learn dogs. I think that's obvious. What I could also do is the following. If I have a small class, let's say I have a small number of images of opossums. You don't see many images on Instagram of opossums, right? I mean, so I don't have many images of opossums to learn from. So what I could do is learn from images of the dogs and cats in order for me to learn what an opossum looks like. And there was a previous talk today talking about representation learning, and neural networks are pretty good at that, is that I can learn kind of an animal will have 4 legs and it's going to have a fur. I can learn all these things from the cats and dogs, and when I see an opossum, I can use that knowledge into that, right? So I want to learn from multi-classes as possible, and the way to do that is by conditional. So what I do, I have my noise, and I'm generating an image of an animal conditional on what I want to generate, right? So instead of doing cats independently, dogs independently, opossums independently, what I'm going to do is going to be learning all of them together, but at every time I put this conditional there, right? So this goes as an input. That's all I'm saying. So when it goes to the discriminator, the condition is passed there too. So we all know that it's a cat that is going through, or a dog, or a opossum. The only thing is that by doing that, I'm learning the weights better for everybody. Okay? So I'm sharing this knowledge, right? So that's called conditional thing. All right. I think we talked about motivation. I think I explained the generative models, the basic idea of generative model, the basic idea of GANs, the generated adversarial neural networks. I think I explained the WGANs and the conditional which I sneak in there. Now it's time to talk about my model, right? So our model is the following. My goal is to generate time series of celestial objects. Yes, it is a little boring, but you know, stars are romantic and nice for us, yeah. Right? Thank you. All right. So, so the first model we did is the following. So there is one big complication in astronomical data, that time series, the times are not regular. And the reason for that is because weather, the Earth tends to rotate around the sun. We have all these problems. So you can't just say, I'm going to always make observations every 1 hour. First problem you're going to have is that day comes, you can't observe, so you have gaps. Second, the weather comes in. You can observe tonight. I missed 3 hours. Okay? Trust me, you go to the telescope, and then the weather comes, and you're stuck there waiting. Okay. So the times are never regular. So we have this problem. So one way of solving this problem is we condition on the times. So we use the times as condition the same way we use conditions for cats, dogs, and opossums, right? Second thing we did is to, the second thing we did, we condition on the class of the star, the amplitude, and the time, right? So we condition on everything we knew about these objects, right? So that's our model. Basically, we're going to generate things fake things by showing some examples first to learn, and then we're going to generate it. So here, the first data set we did, which is a typical thing in this kind of business, is you create synthetic data set and then try to see if you can generate. So we create sine and a soul kind of shape. This is the real ones, and these are our generated data. Looks good, right? Does it look like fake? So the second data set we did is we have realistic data. We have some star light curves, I mean time series from astronomical object. We have from power demand, and we have for ECG 200, which is the ECG data set. All these are taken from the UCF, which is basically standard data sets people use to compare things, right? That's why I call them real, because they're not so real. So the real data sets here, in the case of the starlight curves, we have 80 particular ones. First training class 20, and the second training class size 200, and the test set 100. So here you see the training and the testing. Then we move into the, I mean, this worked very well, which I'm missing the slide that shows you the result, but trust me, it works very well. Now, we move into the real data, which is the Catalina Sky Survey. These are real data, not clean, pristine little data set. This is straight out of the telescope. So the training set is hugely imbalanced. So we have particular stars, we have 30,000 examples, right? And we have objects that we have only a handful of. This is exactly my problem. This is the training sets we facing. So I have training sets that have these eclipsing binary stars, which are very easy to identify, two stars going around and there's eclipses. We have these ones that they're pulsating stars. You can see the light going up or down. But then you come down to here, and basically we have very handful of them, right? So the goal now is to generate things in order to balance these things so I can do my classification and my machine learning, right? So these are the examples of the things we have, the realistic ones. And this is the results. So blue are real one, red are fake ones. Exciting. Yeah. You all think boring blue, boring red. Anyways, so but they look, the red looked like the blue, right? So we also did another test, which is basically when actually to the people that they ran this survey, they happen to be my friends at Caltech, and I told them, okay, I'm going to show you time series of your own survey that you've been working for 5-10 years now, publishing papers with those time series. I'm going to show you my generated ones, and you're going to have to tell me if it's real or fake. And I thought it would be impossible. It would be absolutely slam dunk for him to find out whether they're real or fake, right? Reality is, he was like flipping a coin. He couldn't tell. Right? All right, so that sounds good, but we're scientists, right? You don't believe me when I tell you, yeah, my friend in Caltech told me everything is cool, right? So I can't publish that kind of paper. So I need something more scientific, some more quantitative measure of how well we're doing, right? So there's two ways to do that. So, so I said, why don't we use the Inception network and then call it the Inception Score? How many of you know what is that? It's like, blew my mind, man. This is the kind of thing. I don't know what you're talking about, but you're blowing my mind with this kind of statements. All right, let's explain that. So the basic concept is the following. I want my data. I want to generate data that are very diverse. So that's statement number one. And I want my data not to only be diverse, but to be junk. I want to create good quality data. So back to the cats and dogs, because that's easy to understand. Let's say I want to generate images of animals. I don't want to only create one type of a cat. I want to create diverse images of animals, and that's the statement number one. And the statement number two is that I want to have good quality images. Okay? So if one holds, meaning that I have diverse data, So we expect the distribution of the labels to be uniform, right? So if Y is the label of cat, dogs, etc., then I want to have a uniform distribution of all these things, right? So that means PY should be uniform. If we have high quality of data, it means the conditional of Y given X is sharp. Deep statement, right? So at the end of the day, what we want this and this to be as different as possible. And that's what is the Inception Score. And that came out of Google when they created the Inception network. And that's why I call it the Inception Score. So if I'm going to generate diverse and good quality, the Inception Score should be high, right? Or low. One of the two. Either very high or very low. I can't remember now. Okay. So basically what you do, this is the PY, is big and flat, and this is the PY of X. Why PY of X should be big? Because if I have a good quality data X, I can predict the label, right? That's what it means. Okay. So that's one kind of test we can do. The other kind of test we can do is called TSTR, train on synthetic, test on real. That's what it stands for. So what I'm going to do, I'm going to generate synthetic data, train them, oh, where's my picture? Generate fake data, use the fake data to train now a classifier, and test it on the real one. So that means if I generate real good quality data, my model I'm going to train on this new training data should be as good as training on a real data. Does it make sense? Yep. So that's what we call TSTR. It's cool. So we train on the real one, which the fake ones, which are the blue, and we test on the real ones and see how well we do. All right. So here is the results. So this is the true labels and predicted labels. This is my confusion matrix. And you can see that we're doing very well, except these classes here, they were driving us nuts, meaning that we don't predict very well. The confusion matrix is, we put them in the wrong category. Yeah, we're working on that. There's something there that bothers us because these classes are extremely small and is no learning at all there. Okay. So in the interest of time, let me summarize. We introduced GAN and WGAN, I hope. We convinced you that we need training sets and we need training sets. GAN is a way of generating such training sets, especially for small classes. The future work, in our case, can become better. Those two classes were not doing very well. We're playing around with different ideas. We're trying to put the task, the classifier inside the model to maybe help understand that it's doing badly there. So we want to make it into practical too. We're trying actually to deploy that for the new survey that is coming, the LSST, which is happening in Chile. And we're trying to get this to be deployed at the telescope so we can keep training as data come in and classify them automatically. So that's a goal. And this is my final thoughts is that I've seen people in our part of the world, they're using GANs to generate data, and then they use those data in order to do physical inference. And I think that's not the good way. The way we use the GANs is to generate synthetic data in order to train the model, but the actual inference will happen when we do evaluation. I'm not using the data to generate data and then say, oh, the cosmos is made out of that. That's my final thoughts. This is not related to GAN, but it's just I found it is about segmentation and RCNNs, and I realized it's actually in India. But I think this is the quietest street in India that I have seen. But that guy, did you see that guy? He looks like me. That's how I cross the streets in India. Wait, you have to see it from the beginning. It's very funny. Yeah, this guy, look at him. That's how I am. All right, thank you very much. And I give you this. These are fake hamburgers from the big gun. That's what it's called. All right, thank you. There is one here. There's one here.
Hello. Yeah, so talking about WGAN, empirically has it been found that since you have a better resolution on the feedback, those GANs train faster in the sense now that...
Yeah, absolutely.
So does that happen, or are there any other artifacts that, for example, like empirically speaking, there's no like correlation between that?
Empirically, I can tell you first experience, they work much better than GANs. One thing I mentioned earlier is that there are some problems with how to deal with the fact that it has to be a kind of a particular function. In the original paper, the author says it's a really bad idea to do derivative clipping. So you want the derivatives to be smaller than the value. That's what you want, right? But he said, we're going to use it for now because of the paper, right? And he says, this is a bad idea. And since then, everybody's using that. There's another way of doing the regularizing it. But anyways, the bottom line is that empirically, at least from my experience, they work much better. I never got a case that they work worse than in the worst scenario, they work very similarly, right? I haven't seen a study, someone who's done empirical study which one works better. But okay, the final thought, these cases, they just don't work either, right? But it's not that you try this versus discriminator GAN and the discriminator GAN wins by a lot. Okay? So, and that makes sense if you think about the distances, right?
Hello. So one more question about GANs. So I've been thinking about different applications for GANs, and like one thing you pointed out was solving the issue of class imbalance when you're trying to solve a machine learning problem and you don't have enough samples for all the groups. Then that class imbalance problem can be solved using GANs. The other thing that you had mentioned is like GANs kind of pick up the modal part of the distribution. So when we do data collection, we generally pick up the mode, like the samples around the mode, and then if we train a GAN using that to increase the number of samples, we kind of pick up the modal part of the distribution. So the two things that I wanted to connect was like, and ask you a question about is you mentioned the diversity part about how we have to make certain changes when we train to make sure that we get a diversity of samples from the GAN. And the problem in experiments is that some distributions are fat-tailed. They are not, all the information is not stuck around the modes. So is there a relationship between how we choose diversity metrics and the kind of distributions that we are trying to imitate?
I think that's all good questions. Well, the diversity, you put, again, a regularizer, right? So you put a regularizer with the hope that you're going to do. And as every other regularizer is a regularizer, is not, it's not first principle, right? In particular, this one. So I'm not sure if I know if there is some kind of rule of thumb of what kind of regularizer you're going to put there depending on the distribution you have, right? I believe the best the way to do it is some kind of either cross-validation or generate data and look at them, right? But I don't know if there is some... I think if I understand what you're asking me, if there is any way of knowing how much to penalize given how fat your tails are, right? Is that right? I mean, intuitively, I think should be opposite, inversely related, right? If you have a distribution that is very, is very fat, you want to create as diverse as possible, right? So, but I don't know of principal way of doing it.
Hello. Can you hear me?
Yeah, I can't see you, but I can hear you.
Oh, both my hands are up.
Yeah, good. You're friends.
So my name is Argun Oberoi, and firstly, thank you so much for your lucid presentation. And a testament to that is I almost forgot that I was hungry until your last image.
Oh yes, that's why I put it, so we can get out quickly. But
so my question is on the last point that you touched up on, which I really liked, when you were talking about people making inferences from the synthetic data.
yeah.
I also wanted to ask you, as you mentioned that you use your synthetic data for training purpose. Just from your own point of view as someone researching on this field, what are the risks you feel with what you're doing as well? By that, what I mean to ask is, the synthetic data that you're preparing for training models, what is the risk that you personally tell yourself that, hey, this could be a risk?
Yeah, I think it's an extremely good question, and I appreciate it. It is a little bit, I mean, you have to be careful. Whatever we do, especially we do inference about the real world, I mean, put the warning there, I mean, making bad inference about astronomy is not so bad, right? Okay, so I made a mistake, so what, right? I think this gets much more complicated when we make either wrong inference that affects lives of people, either, health or even, job and a career or kids. I think those are more important. So I think that's what I think you're interested, right? So if I make a mistake on my stars, yeah, whatever, right? But let me answer the question. So let's say, for example, I create a training set that I'm trying to balance my training set, but by creating this GAN, I create other biases, right? These will creep into my inference when I train my models and I apply my models, right? Okay? I think that's where you're getting, right? Is that correct? Or sort of?
Yeah, just something that you sort of...
No, I think I'm totally getting it. I think I can give you an example. Let's say I'm trying to do cats, dogs, etc., right? So, and I create a GAN that all of a sudden, it creates opossums that they look like cats, right? So that means my model that I'm going to learn by using, first I augment my data, and then I use those data to train a model, right? So my model I'm going to train, it depends on the training set, right? So that biases that I introduce with the GAN, with the generator, will creep into my final results. And that I totally appreciate. Now the good thing is that here I can do evaluation, right? I can, if I'm careful enough, and you don't have to be very, very creative here, I can create an evaluation set. In our case, in astronomy, what we did, we go blindly now. After we do everything blindly, and we take some more data and evaluate it, right? So it's totally out of the data set, right? And it's a good, so there I have a good control of how much my biases crept into the inference, right?
Pavlos, you can step out of the spotlight if it's too hot.
No, I like the spotlight. It's my chance. All right, so I hope I answer, and we can continue later, right? I'll be around for...
Yeah, so I had a question here. So like in astronomical data, you were looking at the light patterns, right? So apart from just light patterns, there's a lot of noisy data in astronomy, if I'm not mistaken. Have you, what do you think is the role of things like GAN and AI in cleaning up that noisy data? So you can actually use data that you have, but earlier you couldn't because it was very noisy. But today, using these methods, you can clean it up. Do you think there's applications for that as well? And whereas in astronomy, you've applied all of it?
Yes, I think it's I think that's an interesting application. I think there is a group that works on something like that, but meaning using GAN in order to clean the data before we do something. Yeah, I think it will be interesting. Come and talk to me if you want to work on that. We're looking for people. I told you, there's only 5 papers.
Hi, over here. So you had mentioned that we can solve we can partially solve the class imbalance problem when it comes to machine learning problems and classification. But you mentioned that when there's really high skewness and you really do not have samples for a particular class, your model really doesn't. GANs are still not effective enough.
Yeah.
So what further research has been happening in this area to solve that remaining part of the problem?
Let me say, it's a chicken and egg problem, right? So if I have a lot of data, I can train an amazing GAN system, right? But what's the point? If I have enough data, I can train my model directly. If I don't have enough data, if I go to the very extreme case that I have very little data, you know, it's impossible to train a GAN, right? So that's what they hope is this multi-class thing was going to help. It helped a lot up to a point, but if I only have one example, it's not going to learn, right? So we're trying to figure out kind of ways to do that, but it may not be enough signal. So sometimes you just don't have enough signal to solve the problem. That's the way it is. Right? But as I said, this balance between having enough, not having enough, somewhere between GANs win. Because I can tell you for a fact that if I have enough training sets, we did compare, and there was not helping at all. Because if I have 30,000 examples in this particular of each class, yeah, you can generate as much as you want, but you already have reached the performance you're going to get, right? Okay.
Hello. Yeah. So we'll I know it's super late for lunch. So Pavlos, however, has consented to being what you call it, mocked. So while Pavlos is eating, please do feel free to approach him.
No, I didn't offer that. Leave me alone. I'll be around.